Good afternoon, gentle readers. Today is Tuesday, August 13, 2024. And so this afternoon, from a desk with Ross Finlayson, here again is another episode of Moment and Motion, the mechanics of time. I just made up that last bit. It kind of helps to accentuate that motion is defined as by the carriage of time. I was reading a book a couple months ago, and it reminded me of something that I read yesterday. And what it was about the object sense in the infant. And what happens as it develops is it begins with just being able to tell two things apart, and then that they're different. And then that the persistence of vision, or the five phenomenon, as Wertheimer kind of puts it, begins to set in terms of the time sense and the object sense. And as with regards to, thusly, that it becomes that according to the continuous time series data that all our senses receive, where the auditory and the visual in particular are where much of this is encoded vis-a-vis motion of movements and apsara and this kind of thing, or anything as with regards to structured information in time series data, that it's just a very general and usual concept. And so trying to understand it, it has, of course, a lot of theory equipping it with a wealthy background of all sorts of the mechanics, of the dynamics, of the theory of motion mathematically, and then physically, and then as with regards to all the qualia and qualitative aspects of those things that take part in all the events in the space-time, in terms of this continuous manifold of space-time, which is called the universe, in which, according to a theory of some of histories and some of potentials, and thus least action and a gradient, that it also acts as one thing in terms of being parameterized by time and parametrized by time. Now, I wanted to make a brief note on usage. So some have it that parameterized and parametrized are one word, and some have that they are not, that in different contexts they have different meanings. So when we say parameterized, it's usually as with regards to a constant input to a function. Here we discuss something like, I was coding on my computer Vim in the sequel and Vim in the build all day. I ran about 20 commands, 1,000 or 10,000 different times with different parameters in the inputs, parameterization. Vis-a-vis that a parametrization is a little bit of a concept associated with associating a metric to things, or this quasi-invariant measure theory, the metric of things. So when I see parameterized, then sometimes I'll see parametrized employed in mathematical works in physics, and what it means is a very particular aspect of assigning the metric and the norm to things, which it basically gives a meter stick to a place and a position, and the idea that there's also the same length one far away, however small it might look. So in this manner, parametrized had a particular fixed more meaning, where parameterized, as in all differential systems are one combined differential system in time series data parameterized by time, that being just an implicit, along with everything else and all the rest of its parameters, those constituents of these systems, open and closed systems, here that we mostly fall upon the wave as the object, as the model of change in open systems, according to time, and wavelets and Huygens principle, and when it's no longer Huygens principle, waves beget waves, or they don't, or the attenuation in the floor and this kind of thing. That, in the coherence and coherency of that long-winded, though grammatically correct utterance, we'll begin then to kind of consider some of what goes more into this notion of theory of moment and motion, turns and changes and turns in time. That's about all I've come up with for it. because over the past few talks, what's really been kind of the focus has been this Zeno swath. And so the idea of Zeno swath is the ability to formalize a way that the infinitely many higher orders of acceleration make what's called a hypercube distance. That then for all the different parameters that go into it, or the sliding scales that make it so that you could identify exactly each different given point, its order in all the higher orders of acceleration or deceleration, meeting and parting, starting and stopping, that it falls down from some very highest order of acceleration, the little end, as it were, of this infinite series, like the geometric series, and then finally the big N, which is when everything's constant and it's just 0 to 1 to 0 to 1. The hypercube distance of an arbitrarily dimensioned hypercube, and the distance is 1. So that has been kind of the focus of the talk of the past several talks. And it's convenient that it's sensible because you can just consider it starting that way, that it's classical in the limit, as it were, that it's the same thing for the very simplest case. And again, a kind of trivial example. As it builds and builds and builds, then it just stays in the course of all these different things. Finally, to where the idea is to try to figure out how to model a turn of otherwise a straight path. That here that's been addressed with regards to the hyperbolic, that being an infinitely distant point in infinity, reaching us toward us up to 1, 1, where its change is greatest, and then going up to infinity, a turn, a right angle, as it were, with no corners. That this is beginning to sound contrived, is like that a circle is an infinitely sided polygon. And as with regards to like the interior, the angle of the circle and 2 pi. And it kind of is. I mean, it has to all fall together with the very most usual central fundamental primitives of all the mathematical objects in the mathematical universe, because that's what's given and provided regardless of anything else. And then that this super standard, non-classical, non-standard, if it's infinitary, it's non-standard, with regards to the classical, and which is just, it's linear and finite. That then this super standard way to try to figure out that from infinitely many on down, that it collapses to make a box, is just kind of having at least that it arrives somewhere. Vis-a-vis, it just goes on forever. We know from our theory of the limit that something goes until it reaches, after this sigmoidal kind of approach, that it reaches a limit for sure. And then the infinite limit is that touches when it reaches there at the end. Then the continuum limit is that kind of in reverse, like unfolding to show it's inside all these things as one thing, you know. That is the kind of idea of convergence. It's something that's got an infinitary expression with the terms that reduce as they drop off, yet somehow infinitely many of them add up to one whole thing. Has that as a very rich subfield of mathematics, just trying to figure out what are the laws of convergence. And part of the reason of that is because there are multiple laws of large numbers. And as with regards to whether here that there's 3 definitions of continuity called line reals, field reals, and signal reals, different definitions. Otherwise, most of the time you'll find that everybody will have arrived at the same sort of definition called field continuity, as with regards to Dedekind's Archimedean field from Eudoxus, and one of Aristotle's continuums. But then most other people's most usual next notion of continuity is points in a line between 0 and 1 as consecutive, as contiguous, as only so ordered, as exactly between 0 and 1, as establishing this metric and measure according to a constant uniform parameter in its evolution called time. These line reals, another one of kind of Aristotle's continuums. If you read Aristotle, you find he entertains both these notions. He kind of puts down the line reals because everything according to the tools of geometry work out making constructions that kind of are able to pick a point on the line vis-a-vis that the point in a line is mathematical itself. You can make rational constructions only in the rationals. You don't need all the real rationals, and you can't really say they're closed either. But then that's at least kind of the last thing to say. Well, at the very end, when it's already all filled up, we'll just say it's complete. It kind of arrives that according to deductive inference, that there's only that this line real that has to be first, or there has to be like a continuum as a constant, as a given. That's the way these things are, and it's happily that's the way it is. Why isn't this much more so the curriculum? Well, it's because without that, you pretty much don't have to introduce the entire notion of the infinitary at all. All these notions of the limit in the pre-calculus course, where we're told it's like, yeah, linear motion, forget about it. We're dealing with the same things we were talking about when you learned for classical constructions in geometry, that it's an exercise in application and it's finite, but then it exhausts the things. You learn this. So now you're going to learn all the fundamental theorems of the derivative and the integral, as after given the arithmetic and the properties of inequalities in arithmetic, trichotomy, the ordering of the numbers, and the infinite divisibility thereof, and delta epsilonics, so that we can entertain in the Archimedean field its infinite divisibility, that's why it is so. And then why that's left out of the formal apparatus is pretty much for the same reason. It's just kind of like this necessary super standard extra classical non-standard piece from the beginning that entails this entire kind of leap in the conceptions of things. There's a third form of this continuity, the signal continuity. And so it's very well explored already with regards to something like the complete metrizing ultrafilter, metrizing again, with regards to the signal continuity and the Fourier style analysis, or anywhere that there's integrated infinitely many differentials. Like if the line integral is still just kind of exactly like this line drawing, but this got some special character to its function that defines it. Field and reals and the complete ordered field and the Archimedean field are totally well explored, totally well understood. It's called standard. It's called the linear curriculum, and everybody should know it because it's the same numbers and it's the same schooling that everybody got all through their introduction to mathematics in school. The numbers, the real numbers. And then the signal continuity will be familiar to anybody who's ever been exposed to signal engineering or the information theoretic theorems of Shannon and Nyquist, Claude Shannon and Nyquist, who independently sort of arrived at that when you have the super sampling of a signal of a given frequency, that then if you can double that frequency, then you can reconstruct all the necessary components to give a perfect reconstruction of the signal digitally. And then the idea that it's the same in the analog is as a matter of these definitions of differentiability and definitions of integrability, as we talked about here in past talks, in the descriptive differential dynamics, and also here in moment in motion. Those covered a lot of ground, and most of them were only very, very brief sections of some relevant texts, and a lot of it was just a running commentary establishing a narrative, establishing a linear curriculum in this extra standard, super standard, non-standard yet extra and super standard, extraordinary theory that has 3 replete definitions of continuity instead of just one, and so is better. Because otherwise mathematics would, without having resolved, otherwise these 3 definitions are not simpatico, they're not copacetic, they don't agree with the naive interchange of them, except about their bounds, that they share real values on the real valued lattice. That's where they live. And the results exchange among them make for results in function theory that are just as simple that for uncountability, that there's not a bijection between the integers and the power set of the integers, that there's a function that's a non-Cartesian function, that instead of the anti-diagonal, it's that this line drawing is only diagonal. Can't be reordered, can't be changed. It's just that simple. Then I kind of arrive at. Then the extra bit of bookkeeping goes into that. Yeah, the numbers are a resource and they're infinite, and so you can make use of them however they so fit. But it just so happens that there's some ways that these three different models of the continuous domains fit variously together. This repleteness. So I don't have much more about the hypercube distance, modeling infinitely many higher orders of acceleration and any given particular range of motion in a box, all its inputs. Or Zeno swath, which is along the lines of how is it so that there's infinitely many higher orders of acceleration and arrive at a unit impulse? Dirac's delta function, everybody's favorite first, not a real function. Non-standard, not a real function. Unit impulse function. Width 0, height infinity, area 1. That these kinds of concepts have been brought into this notion of the theory of motion because it's absolutely otherwise underdefined. It's undefined, except that must be how it is so. That otherwise we have the usual Galilean of constant velocity and the usual Newtonian of force equals mass times acceleration, or classical linear, the definition of massy bodies, their acceleration, according to kinetics and kinematics. There's attached and equipped later the theory of relativity. And then as with regards to classical mechanics, then this is about kind of these Newton's zeroth laws, somewhere between Zeno of Elea, who's like, this is my stopwatch, this is my count, you know, these are the times of things, and this is, you know, your first infinite expression, the geometric series, the sum of the inverse powers of 2 that sum up to 1, which you can also build classically as in the limit. That these are the kinds of things that accumulate to then make it so that there is a way to equip the mathematical model of motion with its infinitary complement from the little end of the series with regards to the butterfly's wings and the teacup and the hurricane from that. So, well, let's see, I visit the bookstore, and so I've gathered some more books, so I hope to kind of look through them today. And one of them, and a couple of them, kind of complement the turbulence theory. The turbulence theory was this great and fantastic book I found. And it was from a symposium on the theory of turbulence from the 1960s, the late 1960s. And in it, the airplane engineers have, for example, Forsythian and including stuff as from the nonlinear, but then also a lot of the great initial elements, initial initiatives in the finite element analysis. Sure, we got a model of mathematical motion. Break it down into smaller and smaller and smaller and smaller steps until we can't really tell the difference between this digital, a finite element analysis, and the analog, which is point A to point B. Great, right? So that the turbulence theory then just began to explore the whole idea of shear and transverse shear with regards to the curling and the vorticial, and the idea that those form these wavelets and waves, you know, the energy or what's potential and compressed potential of a sort. I found another book on turbulence theory, so I'm going to be looking at that a little bit. Then some other ones are just about the numerical methods in finite element analysis. And this is like Newton's method, Newton-Coates, Newton and Gregory, who initially came up with a lot of these ways to, like, can we approximate the square root? Yeah. You know, we'll just kind of figure out this way or that way, and then we can compute and estimate what's halfway out. Start computing out there and find if it's too high or too low, and then find its middle and that, and Newton's method is a binary search of a sort with a bit of arithmetic involved. And then there's Coates, who's like, I am kind of the forerunner of differential geometry. So I found a lot of great numerical methods that close forms for things and make some things that are otherwise in the Cartesian pretty contrived and difficult to solve, or resulting in infinite expression, just closed forms, which is great. And then there's where Euler kind of like, sometimes we point to is like, well, the graph theory bit and Königsberg in the bridges and that, or the infinite series and expressions and all this telescoping bit, which is kind of contrived. I mean, there's lots of places you can say is like, hey, thanks for these results in convergence and infinitary expressions, Euler. They're not the geometric series, so they need their own scaffolding. And but you know they run up and out of numbers, and but by the time they get all the way through complex analysis and make the whole Eulerian-Gaussian integral and this and that, and analyticity, that it's like, and it works out here in our diagram of the complex plane on the real square plane, how it comes around. Well, as long as it doesn't get lost, or as long as there's not any kind of sinkhole or anything between this and that. And that it's not the hyper complex, as it were, with rotations and reflections after Le Cartan and the geometric algebras, or Clifford algebras. That the other developments in this part of the theory, bringing that back, then have these numerical methods after Newton and that. Then we have the modern day tour de force was this Runge-Kutta, which now enables one is like, given an integral, it's possible to crunch out in numbers what its value is without analytically solving it by plugging in various forms that would build to it, and then getting out the principal components or the terms that are the initial part of this spigot of terms, one after another, as they kind of pour out of this infinitary expression, which add up that in the first so many terms it gets approximately enough precision, or that within the first so many terms that it reaches approximately narrow enough tolerance, that then it can be said to be close enough for engineering purposes or otherwise application. Then a couple of other of these books are about works in algebraic geometry, or Zariski and Kodaira. So we're going to look at these a little bit and see what happens. This was from Borges. He's a novelist, and it was read here a little bit, and a personal anthology, and I really enjoyed a couple of his stories. There's one particular good one that I'd remember, and it was Funes the Memorious. It was a guy who was like, he couldn't forget anything, and then he just kind of got lost in his memories. Paul Davies' Superforce. This is an effort to figure out the unifications in field theory. Now, the issue with the unifications in field theory is that we got high energy and low energy, or the idea that the super-symmetry is like, well, how fast can we shake it until it's entirely shook up, compared to like how still can it be that will entirely settle down, this high energy and low energy bit. For the energy and configuration of experiment is like, well, we can make the energy of experiment in a 1 mile track that's somehow like tera electron volts, giga electron volts, tera electron volts. Whereas otherwise it's like, we need to like try to figure out a way to listen to the whole universe and find it in like a box or something like that. The energy of the experiment for the configuration of the experiment, that the unification of forces in these kinds of theories is also like, where at the corners do they start to break? Because they kind of stop looking in the middle of a black hole, and it's like, well, where does it come into like linear, inverse, square, cube wall, from where on the one perspective it's spherical and the other perspective it's flat. Then in the middle is like, wow, all I can tell from in here way down beneath the Planck length of time and mass and length, that they kind of become one dimension of these things. Which they do, because in the hologram and the numerical resource, it results in infinitesimal. That these ideas that make up for like the boson theory and the unification of these forces in the high energies, and then being able to estimate, to predict that given particular inputs in the configuration and energy of experiment, that it's possible to compute values where they basically are making up a standing up of each other, the combination of the strong nuclear force, electricity as for charge and magnetism both, but that really as it interfaces these things, kind of like Maxwell's fields isn't a real field, because that's why we have all the potential fields of electromagnetism. The weak force and the electroweak force and gravity are supposed to be these 4 or 5 forces that make up our unified field theory altogether. So the superforce, the idea was like, it's so great that we were able to unify like the weak and strong, or the electroweak and charge, or charge and the weak force, the nuclear force, in terms of these 4 different things, like at the corners of 2 of them or so on. I know that sounds kind of contrived to say that that's a unification of those forces, but in terms of that, then everything's kind of fungible in this quantity called energy for the potential at any given point, in terms of that's supposed to be in the field number formalism for the field occupation numbers, that it's exactly a distinct point, but sometimes it's a region, wave-particle duality, resonance theory. That this is yet a great book to kind of explain what goes on in the thinking of that, but what it would help maybe would be to have it so that it's like when we're talking about unification of fields and forces in theory, it's not just the high energy configuration, it's also the low energy configuration. Besides the near field where everything's classical, then we also have this point, local, global, and total. And then, for example, when Einstein gets for this, the difference between these 2 words, spatial and spatial, that he just kind of slipped out and is like, I'll keep track of them in my writings this way, because everybody else in the world is just going to think it's a typo and write it the same way. It means something different. Kind of like when you make a distinction between parametrized and parameterized. That these are the kinds of things that go on into it, why it's a thing. So anyways, this was considered for a while before, and I'm just kind of going through the stacks a little bit. The story of philosophy is really great. I'm going to look forward to read that a little bit more, Laurent, and all that kind of thing. Let's get this out of the way here. And this is Graustein, the higher geometry. There's much to be gained from this, because he takes geometry and then gets into, like, at the end of each chapter, he's like, and here's like its complementary duals. Here's the outside part that you're going to have to always find yourself solving for. So that the higher geometry is a good thing to have when we want to get figured out these other things that have singular points, the singularities and the singularity theory, because that's the most natural things for the smallest systems where it shows up. Vis-a-vis super-symmetry, which is described, has at least 2 configurations, the high energy and the low energy super-symmetry, which lives. Let's put this down for a moment. So, let's see then. So here's Kodaira. So before I had Kodaira Volume 2, this is Kodaira Volume 1. Princeton University Press. Iwanami Shoten Publishers. Kunihiko Kodaira. Collected works. Here's a picture of Kodaira as a young man. (1975). Born in 1915, Tokyo, where his early years were influenced by Ienaga. Until 1943, Kodaira was interested in several fields of mathematics, including topology, Hilbert space, Haar measure, Lie groups, and almost periodic functions. So I don't have so much use for Hilbert space, but Haar has got some great things going on in the singular. Lie groups are just kind of trivial sorts of modular closed regions, or like, I mean, they have a lot going on, don't get me wrong, but they're kind of, that's just because they're just kind of, what they really should represent is finite groups and is symmetries of any given particular sort, vis-a-vis otherwise continuous. And then for these periodic functions, that it's like that's helping to reflect, and that you can apply the coefficients to a function like that and apply a Lie group to every one of those bounded regions and basically indicate the zeros and ones for it of an arbitrary sequence from all the space of zeros and ones as a series of coefficients in this space of Lie groups and periodic functions. Having that in the analysis can make that, I mean, it's like you can fill up this with whatever you want, and so these functions will fit. That's sensible. Is it fungible? It's like, well, kind of. I mean, every single one of them has got this kind of thing. Was it tractable? It's like, no. Then it gets into like all these different things he's arrived at, how that is so. It is so. Weyl, Stone, Hodge, Weyl. So we think about Stone like stone check compactification, and that gets into the fixed point theory and the point and infinity bit. And then Hodge has got the great thing from algebraic geometry called the Hodge dual. And so when you get the Hodge dual and then the Rham cohomology, that the Rham cohomology, that the Hodge dual and for algebraic geometry is, and it's pretty closely associated with the geometry part of it algebraically instead of the algebra of this as in terms of having a geometric interpretation. That these are some pretty strong influences. Is mathematical development, and last but not least, Zariski, whose book Algebraic Surfaces provided a simulating and fascinating challenge that strongly influenced Kodaira's later work. He graduated first. This turned out to be the start of a United States, Rham, IAS, Princeton, Fields Medal, Japan Academy. So that's just, it's kind of just an introduction to it, you know, that he was an academic type. And he had this great, tremendous output. And so this book has got a lot in it. This being volume 1 and volume 2, those put together make about 1,500 pages, mostly just plain mathematical formula and running commentary in the usual style of the language of the mathematical development. Perhaps the deepest subject of the joint collaboration, Spencer and Kodaira, is that of the deformation of structures on manifolds. Surfaces, complex analytic surfaces, the structure and classification. Betty numbers, Chern numbers, plurigraments, the Italian geometers, complex analytic surgery. So this kind of reflects on before the comment about analyticity and what happens when it's out is this idea of the piecewise and being able to say, okay, for this particular region, we're going to assign a way to make it so that we got boundaries on either side, and from the left and from the right they meet, and then from the outside it's defined as by this overall configuration, and the inside it's defined by this extreme piece, the singularity, or the piece that puts it together, topological surgery, and that being kind of like the point, local, global, and total. A lot of Kodaira's mathematics were put later into things for complex field theory and also for the relativistic field theory. Here we got some. Let's take a look at this. Preface. Über die Struktur des endlichen vollständig primären Ringes mit verschiedenen Radikalquadrat. So the endless rings, infinite, with a vanishing or the nil square. And so when we talk about that, that's in terms of the terms that can be described as be vanishing, or as with regards to those that make it so that those being the nonlinear terms, as it were, that it then describes the ways when there's just a general flow of things, you can generally make the expectation that lines are together. And then that's one of his first papers here from 1937. Über die allgemeinen Zahlenbegriffe und die Zahlenspaltungen der Komplexe. Eine Bemerkung zur Dimensions Theory. Well, that may be kind of interesting. On some fundamental theorems in the theory of operators in Hilbert space. See, Hilbert space is up in the complex, and so I'd rather just leave it alone, because what I want to get figured out is to have it so that, because I'm kind of working from this identity dimension bit, which starts much lower and just has x equals y as like the dimension, and then the x equal y kind of fold up and as to it instead. So it's got something that kind of curls up, that it curled up into, or that it curls up from, for eventually superstring theory, and what that means exactly. And that then the Hilbert space is kind of like, well, it's kind of like we took regular Euclidean space you know and love, and then made it for complex numbers, and we call it Hilbert space. It's like, okay. On some fundamental theorems, on the theory of almost periodic functions in a group, über die Differenzierbarkeit der parametrigen Untergruppe Gruppen, über zusammenhängende kompakte abelsche Gruppen. Now, I need to brush up on my Deutsch or German, because it's one of the languages with French and English that a lot of the mathematics over time, since 150 years ago, has been written in. So that's, I have been studying, so I'm familiar with kind of the parts, the fragments of some of these words, and it's much easier in English and a little bit closer in French. Die Kuratowskische, for Kuratowski, Abbildung und ein Hofsche Erweiterungssatz. So it's a study of these things, the groups and the setups. Über die Beziehung zwischen den Massen und den Topologien in einer Gruppe. So apparently he wrote a lot of his early papers in German, which is part of the part of the way the world was in 1935 or 1937. And then after World War II, he was taken into America. Harmonic fields and Riemannian manifolds. Generalized potential theory. So this is something I most appreciated when I was looking at some of his other works, was generalized potential theory. Because when you study potential theory, that's like, these are all the extra things falling in any possible direction, all together, which must all add up to the end of making one gradient in one direction, compared to like, well, there's one force and it's pushing exactly in one gradient in one dimension. So the sum of histories is whatever those that added up to arrived at, and the sum of potentials is where that's definitely going, and then the linear force is only like, this is its number right here, the classical piece in the middle. So on this page 172, it purports that there's going to be a brief study of harmonic fields and Riemannian manifolds, generalized potential theory. So this might kind of speak to that the idea of potential theory these days is like, well, we're going to add up all these Laplacians. These Laplacians, they're zero, and we're going to call those harmonic functions, and we're going to say that a study of that is a study of potential theory. And as was discussed here, that is not necessarily the end-all, be-all of potential theory. There are aspects in the potential fields, which are kind of here they're framed as the real fields of physics, the fields of potential, all the potentials of the potential energy. That the potential energy is real, and indeed the classical energy that's just what we have always in our formulas in the middle is also some of that. That the idea that it's the harmonic functions in the Laplacians is not the end-all be-all of potential theory, but it is the way that you usually find it framed everywhere, even today, for sure. In our previous paper, über die harmonischen Tensorfelder in Riemann-Roch Mannigfaltigkeiten, we have given the outline of the theory of harmonic fields, i.e. harmonic integrals in Riemannian manifolds, and shown in particular without detailed proof that the existence of harmonic fields of the first kind can be established with the method of orthogonal projections due to Hermann Weyl. We read from Weyl here from the formalization of the real analysis, if I'm not mistaken. And the idea here, though, that harmonic theory is all that adds up to, we talked a lot about that in some of the earlier discussions, as with regards to the nonlinear electromechanical effects and applications and their applications of the potential field, the path integral and their applications in the potential field, and then as with regards to the Dirichlet problem and works of Poincaré and the Poincaré rough plane, and what goes on in terms of then these larger numbers, effects and applications in fields of potential, which on the point, local, global, and total are as of the global and total reflecting on inward, the inner product of this point local. We have considered also harmonic fields with singularities, but the existence theorem for the fields of the second and third kinds have not yet been obtained. We shall give in this paper the proof of these existence theorems, together with all the details of the theory expounded in our previous paper. He's the only author of it, but he's allowed to say ours. In chapter 1, we shall resume the theory of G. de Rham, concerned with the relations between tensor fields and topology on analytic manifolds. So tensor fields are a lot like vector fields, where it's just like a forest of kelp, or in the ocean, like kelp or corals just kind of waving as in a forest of kelp. And so as the currents come past them, they just kind of wave back and forth. Yet they always keep their shape and form and proportion as what they are. So that's like a vector space. And the tensor space is that again, when it's like, well, we have this is out of scale of that over there, but they preserve somehow the affine, the conformal between them. So we don't know exactly how that adds up, but we have to say that like when it gets from here to there, it's always the same all the way across. So tensor field is just a higher level notion of a vector field, and it adds up to say the same thing, because what it says is that adds up to say the same thing. So, then the analytical manifolds just means like it's ever well defined, and otherwise this wavy surface, that it's flat. And so that's always, there's like the metric and a norm everywhere. And then it's analytic, meaning it's like there's not just vortices of infinite, turbidity, as it were, in between. Analytic, these manifolds, the manifold. And introduce the notations so as to make explicit these intimate relations. Everything's related. We shall give the proof of the theorems of de Rham, and thereby show that some parts of his results can be extended to the case of open manifolds. We shall prove the important theorem of Hodge by Weyl's method of orthogonal projections. And so when he proves his theorems this way, then he's going to keep the results that way. And then it just kind of depends on whether he's going to take this theorem that he's proved and use it like in these open systems when he proved it from a closed system, or whether he's going to retrench that and say, now I proved this ceiling for our theory, and so now we can build in the ceiling. Whether he's building a mirror and a bridge, or whether he's building kind of a ceiling to get back to the floor for these theorems. It could be either way. I'm not quite sure, but I believe that he's just basically setting up so they can establish that everything is linear. He's like, it's linear, it's linear, it's linear again. There's a straight line there and back. Have at it, Weyl has proved this fundamental theorem in the case of Euclidean space. His method is based on the construction of the Green's function, which offers great difficulties in our case of general Riemannian manifolds. We use, therefore, elementary solutions instead of Green's function, which can easily be constructed by the method of Hadamard. Various useful formulae for elementary solutions will also be deduced in chapter 3. By means of these formulae, we shall obtain a new proof of a theorem of de Rham cited in Chapter 1. The existence of harmonic integrals of the second and third kind will be proved in Chapter 4. Now, I'll be particularly curious to find out what are these harmonic integrals of the second and third kind, because if the first kind is just these ones of as about the Laplacian, which is only the second order partials in each of these 3 dimensions, or however so many dimensions, equaling 0, then these other ones would be more along the lines of like the saddles and the cusps and these other kinds of particular cases as from topology, which reflect the inflection points that are inflecting opposite ways at the same point, given the path that reaches about them, that makes it so that the partials aren't well defined or well behaved, as according to Hadamard. It might help to interpret that to kind of have a pretty strong background in mathematics, but a lot of this stuff has just been growing in these talks over these past 100 hours or so. So I don't really plan for these kinds of things. I don't have a narrative yet. This isn't a set of notes. It's really just kind of like, it's not like an instruction or a professing. It's like a reader, someone who's just trying to expose somebody to the very vocabulary at all and the concepts at all. It's a little enriched from that, which is when somebody just reads the textbook so that people can follow along and know how to pronounce the words. But that's kind of what it is in the sense of that is a reading. And well, at the same time, there's some definitely stronger connections to the underlying overall theory that make definite opinionated statements about kind of this strong mathematical Platonism, strong logical positivism, a theory of some potentials after a theory of some histories, that keep it kind of coherent and a pace. So Hadamard was mentioned because he introduced this notion of the well-posed problems, like as if we were reading from the Proofs and Reputations or Emile Lakatos, or from the Gonzalez Velasco about the history of the development of the theory of the Fourier style analysis. The existence of the harmonic integrals. We first prove the general existence theorem, which asserts the existence of the harmonic fields with given singularities characterized by the local harmonic fields, i.e. the harmonic fields defined only in a small subdomain of the manifold. In principle, the proof proceeds parallel to the classical case of Riemann surfaces, but the method of orthogonal projections enables us to simplify the proof in some details. Here, there's some mention of projection and perspective as a complement to geometry at all. That geometry is motion, and projection and perspective add up to the inputs. So arrives at from a flat plane of like the visual and visible, vis-a-vis the stereoscopic, the eyeball and the peripheral parallax and this kind of thing, and the sky and optics. This it helps explain also that he's taken some more elementary approaches to what is being built up as the complex over approaches. They're kind of overbuilt, and he's finding some very fungible fields in that. The existence of the local harmonic fields is not trivial, as in the classical case of Riemann surfaces. We first prove the existence of the local harmonic fields of the third kind, and then obtain those of the second kind by a limiting process, which can be considered as a sort of differentiation. The method of the orthogonal projections will be applied here also very effectively. In the last section in Chapter 4, we shall show that in a neighborhood of an isolated singular point of finite order, every harmonic field can be expanded into a sort of Laurent series, Laurent, Laurent series. In the last chapter, we shall consider the relations between various harmonic fields in a closed Riemannian manifold, and show that they hold the reciprocity formulae and the generalized Riemann-Roch theorem, just as in the classical case of Riemann surfaces. Now, I've heard of that before. I'll have to study it a bit. Laurent series. In the case where the dimension of the manifold is an even number, we can moreover define a kind of analytic differentials on the manifold and give the complete analogy to the classical Riemann-Roch theorem. ROCH, Riemann-Roch. This will be shown in another paper. in order to clarify the relation between our generalized Riemann-Roch theorem and the classical one, we shall finally deduce the classical theorem from our standpoint. Our whole theory may be regarded as a generalization of the classical potential theory. See, this is great because it's defining that the field, the potential overall is the general. And so he's helping to establish that he's building it out this way. And then also he's kind of bringing it back in a bit more to the real and the Euclidean, saying is like, from here it's like, and it's this way. So I feel like there could be a very strong affinity between some of these kinds of developments and what goes on with the identity dimension. And for example, in the even fields, you notice he made the particular comment that it was when the signs are the same, so when the functions are negated, that they maintain these symmetrical, like the negative a is negative a plus b is negative a minus b, or this kind of thing, even and odd functions. Whereas with when you take the powers of something, that it maintains a sign or some other characteristic of the thing. Even and odd is the general idea, but really about just the modular, and when it's mod 0, it's the same. That this is the kind of thing that in his elementary approach, I'm even trying to take even a more elementary approach, this deconstructive account. So I'll be happy to look into this a little bit more to try and help make it so that this has a very particular attachment to the deconstructive accounts being discussed here. Our whole theory. The famous book of Weyl, Die Idee der Riemannschen Fläche, has always served us as a precious guide. So he's talking about, Weyl has a paper about an idea of the Riemann manifolds. Finally, the author wishes to express his cordial thanks to Professor Einaga for his constant encouragement and interest in this paper. So then this chapters, there's 16 sections and 5 chapters. Fields of tensors and tensor densities and analytic manifolds. Harmonic fields and Riemannian manifolds. Fundamental theorem. Harmonic fields of singularities. Harmonic fields and closed Riemannian manifolds. Then he describes how he builds up to de Rham's theory. So in his terms, he's like, now I got cohomology, and now I got duals. Now I'm going to build this out with the things I developed and these other things. And it's fantastic. So now I have both volumes of Kodaira's collected works. So then this other thing, we might not get much look into the turbulence. I want to kind of look at the turbulence and then these numerical methods books, but what we'll probably look at for a while instead is Zariski. Because what I would like to establish is that he's considered as a great influence in the field and for some particular things, that this is a collection of Zariski's papers. And so now I have another new book to go find because this is volume 2 of Zariski's collected papers. So I'll be interested in finding the other volumes of this series. And I'm not for any particular reason, because I don't necessarily find myself needing something to know about the elliptic functions and elliptic curves. It's like, well, I don't really care so much that I'm studying modern cryptography and modern crypto systems with regards to the totally widespread use of elliptic curve cryptography, that I'd be interested in finding, for example, stronger or weaker examples of applications of elliptic curve cryptography, just like I'm not too interested necessarily in finding stronger and weaker applications of prime factorization of large primes, or this kind of thing with regards to the ubiquitous deployment and installation of very well-known, defined, and given algorithms according to the mathematical properties so guaranteed by these things, that it's not like I really just want to figure out a little bit of, an analytic basis for something like the elliptic curves to make it so that That nobody will know what happened if somebody presses the big delete button on crypto. Not my interest, but I'll be curious to see what else here is in this Zariski's collected papers. Holomorphic functions and linear systems. So the holomorphic function, you can think of it as a lot like a singular function, because holomorphic is kind of like the holistic, and it pulls it together. Like the hologram is this idea that the multiple dimensions are somehow encoded in a way that maintains a tensor product between that and the higher dimension. And then it's encoded, these relations in a path, and the one is a path in the other. And so when holomorphic functions and linear systems are these two kind of opposite things. Because a linear system is like an eigensystem, and that's something that I need to understand a little bit better over time in terms of the determinantal forms, the orthogonants, the cumulants and the orthogonants, determinantal analysis, these being sort of lesser explored subfields of the linear algebra since the time when they had a great thing going on in like the 1930s to the 50s or whatever, and then they pretty much were cornered and been gathering dust. But what they do is that they're extensions of linear analysis for after the determinants, which enables one to make inner products of things and compute a lot of different things of the character of functions by setting them up in the matrix and just drawing the diagonal and reading them off. Then there's the cumulants, and the cumulants are basically circles around the matrix, and those adding up, and they have to do with like moments in the moment generating function. And then the orthogonants are another kind of higher level structure just above the matrix in this determinantal analysis, which is so widespread in this eigenfunctions, eigensystems, and linear analysis, linear algebra, that the orthogonants is another way that you can get into some stuff in that, which will again take some of this stuff that was pretty much impossible to solve, in fact by some naive views impossible to solve, and it's crunched. That's a thing. Edited by Artan and Mumford. Zariski is professor at Harvard. And the series is edited by Giancarlo Rota. And it starts with Loewner, Loewner, Theory of Continuous Groups. Zariski, Volume 1, Foundations of Algebraic Geometry and Resolution of Singularities. So when I was reading this Singular Integrals book, Neri, the other day, that was really great, because then that's phrased up in terms of functional theory. And he's like, yeah, complex, I got your complex. But that as well, he gets into like the adjoints, and this thing's going on in the adjoints or the adjunct. And those being so relevant of these duals, and the ability to figure out what's going on was like, well, everything is going great, and now we got a corner, and it's like, well, here's how it goes around the corner. Those are the kinds of things. Collected papers of Rademacher 1 and 2. The Art of Counting by Paul Erdős. Oscar Zariski's Collected Papers Volume 2. This volume here. Here's a portrait of Zariski. Copyright 1973, MIT. Contents, reprints of papers. Quelques questions concernant la théorie des fonctions holomorphes sur une variété algébrique. Some questions concerning the theory of functions that are holomorphic or holomorphic functions over algebraic varieties. Theory and applications of holomorphic functions on algebraic varieties over arbitrary ground fields. Sur la normalité analytique des vérités normales. The connectedness theorem for birational transformations. Reducible exceptional curves of the first kind. Postulation des genres arithmétiques. So we don't have, there's not too much more time in one of these usual brief videos. So what I'll just look to, now linear systems, the Riemann-Roch theorem and applications is all a part 2. So that's something definitely to study for. To compute the dimension of a general linear system D on a complete normal variety X, and especially to consider the behavior of dimension n D as n grows. So it's a hypercube bit. The one here is like coming down from that, and then its distance is 1. So I got the answer. It's 1. The other is to apply the theory of linear systems in the two-dimensional case to obtain results on the birational geometry of surfaces and on the classification of surfaces. All right. It's funny, he says, in relation to his previous work, this research was, I believe, something like a dessert. I imagine he meant desert, but maybe he meant dessert. Hey, have a great day, everyone. Good day, gentle readers, fellow earthlings.